You buy a car for nearly $50,000, and just 10 years later, it enters a quiet secondary industry that few people ever see. More than 90% of its material still holds significant value, especially the windshield glass and rubber tires. The glass is stripped of its PVB layer and returned to a clean, reusable form, while the tires are crushed and separated to recover steel and produce rubber granules used in roads and infrastructure. A vehicle that seems to have reached the end of its driving life still carries materials ready to begin a new journey across multiple manufacturing sectors. In this video, I'll take you inside that transformation, where the value of an old car is reborn to support the next generation of infrastructure and industry. The rebirth of every vehicle begins right at the receiving area, where end-of-life cars are recorded and documented. Before entering the processing line, technicians inspect the VIN, check the battery condition, measure any remaining fuel, and identify components that could pose risks during dismantling. From there, each vehicle is classified based on its dominant materials, level of damage, and the potential for parts recovery. This data determines the exact handling route, whether the car will be dismantled manually, separated by material, or sent directly into an automated depollution and metal recovery line. Everything starts at this receiving stage, the point where an old car officially leaves its operational life and steps into a completely new cycle of material regeneration. The dismantling process begins with removing every remaining fluid inside the vehicle. Technicians open designated drain points to extract engine oil, transmission fluid, coolant, brake fluid, and any leftover fuel in the tank. All of it is routed through separation and filtration systems to prevent environmental leakage, while recovering whatever can still be reused. Only once the car is completely dry can mechanical disassembly safely take place. The most accessible components are handled first.
The battery, starter motor, alternator, ECU, sensors, and other electronic modules. The battery, starter motor, alternator, ECU, sensors, and other electronic modules. The battery, starter motor, alternator, ECU, sensors, and other electronic modules.
Next, elements such as seats, the dashboard, interior plastics, and other non-metal components are removed using hand tools or hydraulic-assisted systems. Depending on the vehicle's construction and how tightly each piece is fixed, each layer of components is carefully peeled away in sequence,
leaving behind the frame and larger assemblies ready for the specialized processing stages that follow.
Once the smaller components have been removed, technicians move on to separating the wheel assemblies from the vehicle. A hydraulic locking system lifts the car off the ground,
creating clearance for them to loosen the lug nuts and release each wheel from the hub.
Every wheel assembly is then taken to a dedicated sorting area. The rims, whether aluminum or steel, are inspected for bends, cracks, and surface wear. Those that remain intact are kept for resale in the spare parts market, while distorted or heavily worn rims
are placed directly into the metal recycling stream. The rubber tires are processed separately using a bead breaker,
a specialized machine that forces the tire's edges away from the rim without damaging the rubber structure. Each tire then undergoes a quick assessment. If the tread is still thick enough and there are no tears, it may be reused in the second-hand market. The majority, however, will be sent to the tire shredding line. Separating rims and tires at this stage ensures each material stream follows the correct recycling route, minimizing contamination and reducing loss. The windshield is one of the most challenging components to handle,
because it is built from two tightly laminated layers of glass, fused with a flexible PVB film in between.
Before removal, technicians cut away the rubber seals and the urethane adhesive surrounding the frame to prevent any deformation to the vehicle's body.
A specialized cutting wire is then fed behind the glass and tensioned along the entire perimeter to separate the adhesive bond.
Once the bond is fully released, the windshield is lifted out using a vacuum lifter to prevent uncontrolled cracking. The intact glass panel is then placed onto a dedicated rack, where it will later undergo PVB separation in the specialized recycling stage.
Meanwhile, The windshield frame on the vehicle is inspected to ensure no adhesive residue or glass fragments remain. Before the car moves on to the next step of the processing line. Once the tires are removed from the vehicle and separated from their rims, they are transported directly to a dedicated staging area
to assess wear, tearing, deformation, and whether its structure is still intact. Workers also record the size, type, and level of damage.
Since each category of tire has different reuse potential and requires a distinct handling path, these staging yards often span thousands of square feet, designed like organized rubber fields, with designated lanes and storage zones to prevent material mix-ups. Tires are stacked in moderately tall rows to maintain fire safety and minimize water retention, a factor that attracts insects and increases contamination risks. Thermal sensors and surveillance cameras are installed throughout the area to detect smoldering heat spots, one of the inherent hazards of waste tire storage. After being collected, cleaned, and stripped of any foreign objects, the tires are sent directly into the plant's continuous shredding system. Here they enter a full deconstruction process,
breaking down rubber engineered to withstand heavy loads and thousands of miles of friction into reusable granules to separate its three primary components: rubber, steel belts, and synthetic fibers. An automated conveyor feeds the tires into high-capacity shredders. Ultra-durable alloy shafts rotate at high speeds, generating cutting and tearing forces powerful enough to break apart the rubber structure within seconds. In many modern facilities, these systems are strong enough to process whole tires without any pre-cutting,
producing rubber fragments just a few millimeters in size after the very first shredding stage. Throughout operation, a low-pressure water spray system runs continuously to cool the cutting blades,
reduce friction, and prevent ignition caused by extreme heat, a constant concern in rubber shredding environments.
At advanced facilities, this process can be enhanced with cryogenic shredding. Tires are chilled with liquid nitrogen to around -300 degrees Fahrenheit, making the rubber brittle and easier to fracture.
Once the material reaches the required fineness and technical standards, it is transferred into a hot air drying chamber, where dry airflow removes all remaining moisture to prevent clumping during transport.
The rubber is then cooled and packaged in a sealed environment to preserve its natural elasticity, the property that gives rubberized asphalt its performance advantage. The rubber is then cooled and packaged in a sealed environment to preserve its natural elasticity, the property that gives rubberized asphalt its performance advantage, ready to be transported to manufacturing facilities. And it is at this transition point that the true value of recycled rubber becomes visible.
One of the most efficient and sustainable applications of tire recycling worldwide, and improving resistance to cracking. Once the stream of recycled rubber has completed its journey, the next material story emerges from a very different corner of the dismantling yard: automotive glass. Multi-layered windshield panels are collected separately from the moment they are removed to prevent breakage and contamination. After being taken off the vehicle body, they are moved to a dedicated staging area where each sheet is placed onto steel racks to prevent warping or cracking.
Workers clear away dust and fragments, then inspect the condition of the PVB layer sandwiched between the two sheets of glass.
Because this transparent film determines the entire treatment process that follows. From the staging area, windshields are sorted according to cleanliness, fracture patterns, and how easily the PVB can be separated. These initial data points form the foundation for entering the glass recycling stage.
It's a process that demands a tightly controlled combination of mechanical force, thermal treatment, and precise material handling.
After the windshield has been stripped of its frame and separated into individual panels, each sheet is placed onto a conveyor. The shredding speed is calibrated to generate just the right cutting force, strong enough to break the bond, yet controlled enough to keep the glass from becoming excessively fine.
Where airflow and continuous oscillation allow the lighter PVB layer to separate from the heavier glass particles.
The PVB is collected and diverted into its own processing stream, while the cleaned glass moves through magnetic separation. And a final air-blowing stage to remove remaining fine dust. The finished product is glass cullet, clean, uniform glass fragments, free from polymer residue. Fully suitable for remelting in industrial glass production furnaces. Once the glass has been completely freed from its PVB layer and broken down into the cullet, the material is fed directly into an automated sorting system. First, a vibrating conveyor spreads the cullet into a thin, even layer so optical sensors can scan every particle. Laser readers and high-speed cameras identify color, particle size, and any remaining contaminants. Non-compliant pieces, such as oversized fragments or particles containing metal or paint, are precisely diverted out of the stream by targeted bursts of compressed air. The qualified cullet then passes through magnets and an eddy current separator to ensure that no microscopic metal pieces remain. Finally, the glass is gathered into consistent purity batches, ready to be melted in glass furnaces as feedstock for the next generation of automotive glazing.
When the clean batches of cullet are fully collected, they are transferred to the mixing area together with silica sand, limestone, and a small amount of sodium carbonate.
The dry ingredients are weighed to precise ratios and blended in a sealed conveyor system to ensure uniformity. A critical fact. Immediately afterward, the entire mixture is fed into a continuous melting furnace, where temperatures can exceed 2,500 degrees Fahrenheit. Under this intense heat, the cullet lowers the melting point and reduces energy consumption, while fully integrating with the other minerals to form a homogeneous stream of molten glass. The molten material is held in a controlled state within the furnace chamber, preparing it for the forming and flat drawing processes that follow. When the molten glass mixture reaches the required level of purity, the stream is directed into a bath of molten tin to begin the float glass process. Here, the hot liquid glass spreads across the surface of the tin, a metal with a higher specific gravity point, forming an exceptionally flat layer under the combined effects of gravity and surface tension. The molten glass gradually expands into a continuous ribbon with consistent thickness and flatness, without the need for any mechanical molds. The ribbon then moves into the annealing zone, where the temperature is lowered in carefully controlled stages to release internal stresses. This controlled cooling process gives the glass the strength and optical stability required for automotive applications. Once it reaches the appropriate temperature threshold, the glass ribbon is drawn out of the annealing chamber and fed directly into an automated cutting system.
Sensors precisely measure width, length, and flatness. After which, industrial blades divide the ribbon
into standardized sheets, ready for bending, applying a new PVB layer, or shaping according to specific windshield designs. When the flat glass sheets exit the float line and are cut to their required dimensions, they are moved into the bending area,
the stage that determines the final shape of an automotive windshield. Each sheet is placed
onto a precisely curved metal mold and passed through a heating chamber at roughly 1,000 to 1,150 degrees Fahrenheit. With minimal optical distortion. Once the shape stabilizes, the sheet undergoes controlled cooling to lock in the curvature and prevent internal stress from forming. After bending, the two curved sheets are transferred to the PVB lamination zone, where a transparent, impact-absorbing PVB film is applied. A layer of PVB is evenly laid between the two glass surfaces, and the entire assembly is placed into a vacuum chamber to remove trapped air. From there, the laminated stack enters an autoclave, where high pressure, combined with temperatures around 230 to 275 degrees Fahrenheit, fully bonds the PVB to the glass. The result is a unified windshield with high structural strength that will not shatter into sharp fragments on impact. Ready for its final quality inspection before being installed on a new vehicle. From a vehicle that has reached the end of its operational life, rubber tires and windshields may seem like difficult-to-handle waste.
Yet, through every stage, from dismantling, shredding, separation, and cleaning,
to melting and reshaping, these materials are reborn into something with real value. Rubber that strengthens road surfaces, and glass that becomes the next generation of automotive glazing. Each step in that cycle shows how recycling industries not only reduce the burden of waste,
but also create strategic raw materials for transportation, infrastructure, and manufacturing.
and that is the journey you've just followed. How materials that appeared to have reached their limits become the foundation for the next generation of vehicles and structures. If you want to explore more of the quiet, powerful technologies reshaping materials behind every major industry, stay with me in the videos to come.